This lesson is on compound interest. You will get a chance during this lesson to use what you've learned about exponential functions, because you'll see that compound interest is an application of an exponential type function. Before we get into compound interest, I want to remind you of the simple interest formula that you probably learned some time ago. Recall the interest formula is I equals P times R times T. The I, of course, in this formula stands for interest. P is principal. Now remember, we use that word to indicate the amount of money that we either invest in an account, or if we're borrowing money, this would be the amount of money that we borrow. R is the interest rate per annum. Now per annum is just another way of saying yearly or annual interest rate. And then T is time, and you'll notice I've said here in years. If we're given an interest rate in years, then our time also needs to be in years. So all this formula does is if we borrow, say, $1,000 at 5% for 2 years, we would multiply these together to get what we call simple interest. Now I have for you a definition of compound interest. Compound interest is interest paid on previously earned interest. Now, just as a quick example, let's just say that we put $1,000 into an account, and so that's going to be our principal, that our annual interest rate, let's say, is 5%. And remember, as we use percents, we will write those as decimals, so 0.05 would be the equivalent decimal. And let's say that this interest is paid quarterly. Do you know what quarterly means? That means 4 times a year. So 4 times a year. Okay, well, if I calculate my interest on $1,000, so I equals the principal, times the rate 0.05, times the time. Now recall the time needed to be in years. That first time, the money will only have been in there for 1/4 of a year. So multiplying 0.05 times 1,000, we have 50 times 1/4, and I'm just going to take my calculator and divide 50 by 4. And what I have here is $12.50. Now remember, this was interest. Now, if I leave that interest in my account, I will have a new balance in my account. My new balance will be my original $1,000 plus this $12.50, or it will be $1,012.50. Now, the next time that they're going to pay me interest, they're going to pay me interest on this amount, not on the 1,000. So they would calculate with a different principal. So what they've done now is they're beginning to pay me interest on this previously earned interest. That's what we mean by compounding or compound interest. Now, what I want to do is to take another example, and we're going to carry this out just a little bit farther. In this particular problem, it says $1,000 is invested at an annual rate of 6%, compounded quarterly. The question is, how much will be in the account at the end of 1 year? Well, one way we can do that is to just go through and calculate interest. So if this is compounded quarterly, they're going to pay my interest 4 times, aren't they? So let's do interest for that first period. We're going to have $1,000 times our 6% as a decimal, 0.06, times 1/4 of a year. I'm just going to pick up my calculator to do that calculation right quick. 1,000 times 0.06, and then we're going to divide that by 4, and that gives me $15 worth of interest. Now, this is the first time, right? Okay, the second time that they pay me interest, I'm going to add this 15 in with that 1,000. They're going to pay me interest on $1,015 at 6%. Notice again, my time is still going to be 1/4 of a year, isn't it? So let me put in my 1,015 times my 0.06 divided by 4. This interest is $15.23. Now I'm rounding off because that's what they would do at the bank. Now this goes in with that 1,015 that I already had in there. So now I have 1,030.23, don't I? So the third time we calculate interest, it will be on 1,030.23 at 6% for, again, a fourth of a year. Let me do that right quick. 1,030.23 cents times 0.06. Again, we're dividing by 4. So this time the interest amounted to $15.45. Okay, let's add that to that 1,030.23 to get our new balance. Let's see, it's going to be $1,045.68. Now we're going to calculate interest one more time, right? 4 times a year. So this time on $1,045.68 times 6%, again times 1/4 of a year. Give me just a second here to push my calculator keys. This time the interest is $15.69. Again, that's going to be added to the $1,045.68. I believe that's going to give me $1,061.31 in that account at the end of 1 year. Now, I wanted to go through this example like that with you for you to see how complicated it can become in terms of tedious steps if we try to calculate each time the interest, add it in, calculate interest the next time and add it in. Fortunately, we have been able to come up with a formula that will do this compounding for us. We're going to look at this compound interest formula and talk about the different parts of it, and you'll see that it has the form of an exponential type function. Okay, let's look at this compound interest formula. A equals P times the quantity, 1 plus R over N, and that quantity is raised to the N times T power. Now let's notice here, A is the amount after T years. Now what I mean by that, this is going to be the amount of money that's in the account. So that's not just interest here. That includes our original principal. P is the original principal, that's this number here. R is, notice, the annual interest rate. T is the number of years, and N is the number of times compounded per year. So if we compound quarterly, then that would be 4 times during a year, wouldn't it? Now what I want to do, since we've got this formula, is go back to this problem that we just looked at. It said $1,000 is invested at 6% compounded quarterly. How much will be in the account at the end of 1 year? What I want to do is to rework this problem using this new formula. I want to know how much is going to be in the account. I want to know A. So I'm going to write A here. My P, my principal, was $1,000 times 1 plus my annual interest rate was 6%. I'm going to write that as a decimal, 0.06. I'm compounding quarterly. That means 4 times a year, so this N right here is a 4. And then up here I have N, which we said is 4 times T. Well, I said 1 year, so 4 times 1 gives me an exponent of 4. Okay? Now, let's do a little bit of simplifying. I'm going to kind of take this a little bit at a time. I'm going to take my calculator and divide 0.06 by 4, and then I'm going to add that 1, and this quantity right here becomes 1.015, and that is raised to the 4th power. Now, with our calculator, remember your x to the y key? We can put in this base and raise it to the 4th power with that x to the y key. So I have 1.015 in my calculator. I'm going to use my x to the y key and put in an exponent of 4. I'm going to hit equal to complete that, and then I'm going to multiply. Notice this says times my 1,000. And what I show here on my calculator is 1061 and 36 cents, $1,061.31. Look at the answer that we got when we did that by hand. The only difference is what? Up here we rounded off and got an extra penny. So this formula is very, very accurate. It will sometimes disagree just a little bit, But this formula is actually what most of our institutions use when they compute compound interest. So again, I want us to pay attention here. T is the number of years, N is how many times we're compounding. This is our annual interest rate, how many times we're compounding, original principal, and this gives us the amount in the account. So we're going to use this formula now to do some example problems. If $2,000 is invested at an annual rate of 7%, how much will be in the account at the end of 10 years if interest is compounded monthly? Now, what I want to do, my original principal is $2,000, isn't it? My interest rate R is 7%. I'm going to write that as a decimal, 0.07. Now, what is N? How many times during the year are we going to compound? We're compounding monthly. That would be 12 times a year, wouldn't it? Now, T is how many years? At the end of 10 years. So we've identified T as 10. Now, again, let me slide this formula up here because I know you've not had a chance really to learn that just yet. We're going to apply this formula. We are looking for A. So let me write the A down. My P is 2,000. Put a parenthesis, 1 plus. My R is 0.07. My N we said was 12. And up here I want to multiply N times T. Well, 12 times 10 is 120, isn't it? So this is what I want to use to calculate my interest. Now, I'm going to slide my calculator up here if I can get it where it's not glaring too much and show you how I can kind of do all of this stuff together. I'm going to start inside the parenthesis here just like we normally do. So I'm going to take 1 plus my 0.07 divided by 12, and I'm going to hit an equal to complete that. Now, I can be confident that my calculator will give me the correct answer here because it's a scientific calculator. It knows to divide before it adds. Now, I have my base. I'm going to use my x to the y key and raise that to the 120th power. And then I'm going to multiply by this 2,000. That's over here. And what I have here is that A is $4,019.32. Now, actually, with the calculator, I could do this exactly as this is written if I choose to use my parenthesis keys. Let me show you. I could go ahead and put in my 2,000 and hit my times. Then just use an open parenthesis, 1 plus 0.07 divided by 12, close the parenthesis, hit your x to the y to do the exponent, 120, and then hit equal to complete that calculation. And you'll see that I have the same exact answer there. Now, I really encourage you to take your calculator. You may want to pause your tape at this time and practice with your calculator to see if you enter things exactly like I do in this problem. Keep in mind that some calculators you do things in a slightly different order. But if it's a scientific calculator, this sequence should work for you as well. Do you see how nice that formula is, that we can very quickly find out how much is going to be in the account at the end of 10 years? Think about how many times we would have to have computed interest to do that the old way. Every month for 10 years. That'd be 120 times, actually, as it turns out. So this is really a nice formula. Okay, well, let's take, again, $2,000. This time we're investing at that same annual rate of 7%, but notice how much will be in the account at the end of 10 years if interest is compounded daily instead of monthly. Well, let's see. Our principal is $2,000. Our annual interest rate R is 7%, 0.07. N is the number of times that we compound. Now, when we compound daily, you know, of course, that some years have 365 days and some have 366. Normally, when you do calculations like this and it says daily, you just assume a 365-day year. So that's what we'll assume here. Now, our time, again, is 10 years, isn't it? So if you recall our formula, A equals our P, 2,000, times the quantity 1 plus the R, which is 0.07, divided by the N, 365, and that is raised to the 365 times 10 power. Of course, you can do that multiplication in your head and know that that's 3,650, can't you? Okay, well, let's go to the calculator, and I'm going to do this sort of like I did that last one a while ago. Let me slide this over. Hopefully that's not too much glare for you. I'm going to go ahead and put in my 2,000 times. I'm going to use my parenthesis, 1 plus 0.07 divided by 365, close my parenthesis, exponent 3650. I'm going to ahead and multiply by 10. Now hit equal to complete that calculation. Now my calculator reading is giving me $4,027.24. Now, a while ago when we did this monthly, let me show you that answer. We had $4,019.32. So notice we did get a little bit extra interest here by having our interest compounded daily instead of monthly. Okay, well, let's look at this problem. At 6% compounded quarterly, how long will it take for $2,000 to triple? Well, now this problem is a little bit different. Let's kind of identify what we know here. Of course, 6% is our interest rate, R, isn't it? So let's write that down. R is 6%. We are compounding quarterly, so we know N is 4. Notice the question, how long? We don't know. T, that's what we're trying to find out, isn't it? But what is this 2,000? We want this 2,000 to triple. So 2,000 is our original principal. And what do we mean by wanting it to triple? That means at the end of this time period, however long it takes, we want the amount to be 3 times this, or $6,000. Well, we just have a different missing part, but we can still use that formula. Let me write the formula for you here again. A equals P times the quantity 1 plus R over N to the N times T power. Now, this time we know A is 6,000. P is 2,000. I have 1 plus my R, 0.06, divided by N, 4, equals. Now I know N is 4, but I don't know T, so that's just going to have to be 4 times T right there. Well, look what we have right here. This, of course, is going to be a constant. Look where your variable is. It's up there in that exponent, isn't it? If you have done that lesson working with properties of logarithms, you learned how to solve an equation where the variable was up there in that exponent. Now, what I'm going to do in this problem, because I have this quantity out here, we're going to divide by that. First of all, we're going to divide both sides by 2,000 to get rid of that coefficient right there. This will cancel. And of course, 2,000 divided by 6,000, or 2,000 divided into 6,000 is 3. So I have 3 equals. And while I'm here, I'm going to go ahead with my calculator and do this part. So I'm going to do 1 plus 0.06 divided by 4. That number is 1.015, and that's to the 4t power. Now, do you remember how we used logarithms in that last problem or last lesson? We're going to take, let's say, the natural logarithm on both sides. The natural log of 3 is equal to the natural log of 1.015 to the 4t power. Now remember, once we have a logarithm, we can bring the exponent down. So the natural log of 3 is equal to 4 times t times the natural log of 1.015. Now, notice this says 4 times t times that logarithm. Just to help you see this a little bit better, I think what I'm going to do is write this like this. I have 4 times the log of 1.015 times t. All of that is times t. Do you see that? Then to solve for t, I just need to divide that natural log 3 by 4 times the natural log of 1.015. Now, I'm going to caution you here that you be very careful how you enter this in the calculator. We need to do this multiplication before we do the division. So we're going to need to use a parenthesis down here to group that. So I'm going to do the natural log of 3 using my alien key on my calculator, divided by, I'll use a parenthesis, 4 times the natural log of 1.015, close my parenthesis, and hit equal to complete this calculation. Now, I have this decimal in the display of my calculator, and it goes on for a few more decimal places. Now, we will want to round off, won't we? Since this interest is compounded quarterly, we want to be sure that we round off far enough that we have completely gotten enough interest for us to have that $6,000. So notice this part right here, 18 4/10 is not quite 18 and a half years, is it? But notice that we would have to get up to that half of a year in order to get that interest paid that second time during that last year. So what I'm going to put here is that t should be 18.5 years. Notice even though that's not a 5 to cause me to round up, I need to go on up to 18 and a half years so that they will compound my interest. Now, as you've seen here, we just substituted into that normal formula that we had, but because our variable ended up here as an exponent, then we had to work a little bit harder with our algebra and go back and use our logarithms in order to come up with that equation. Now, we have talked about compounding quarterly and monthly and even daily. There is also what we call continuous compounding. Now, look at this formula for continuous compounding. A equals P times E to the RT. Now, that E right there is our familiar 2.718 E that we've learned about in the past. You can actually refer to your text if you'd like, and I believe in there they show you how they sort of arrive at this formula. That's not the purpose on this tape. On this tape, we simply want to learn how to use this formula. If we are compounding continuously, that means even more often than every second. And of course, that would be difficult to work without a formula such as this. Notice in this formula, A is the amount after T years, just like it was in that previous formula. P is the principal, R up here is the annual interest rate, and T is the number of years. Notice we don't have to have an N in this problem because we're compounding all the time, not a certain number of times per year. Let's see how we can use this formula to solve a problem. If $5,000 is invested at an annual rate of 5.25%, how much will be in the account at the end of 15 years if interest is compounded continuously? Now, as soon as I notice that it says compounding continuously, then I'm going to think about that new formula. Let me write that formula down for us to look at here. A equals P times E to the RT. That's the formula that we're going to use. Now, let's identify what we know. $5,000 is being invested, so that is our principal, isn't it? We have an annual rate of 5.25%. Now, remember, we need to change from percent to decimal, so this decimal needs to move to the left. So our interest rate is 0.0525 as a decimal, and we know our time, T, is 15 years. Now, let's go to our formula. We're going to find A. Our principal is 5,000. We have E, R times T. Now, I'm just going to write that as 0.0525 times 15. Now, you could, of course, go ahead and multiply that out if you want to, but I'm going to show you on our calculator that it's not necessary that we do that. Okay, let's go to the calculator. I think I'm going to have to scoot this over so it doesn't glare too much for you. I'm going to go ahead and put in my 5,000 and hit my times button. Now I'm going to get my e, so I need to get my e to the x. Now, because I'm going to do a calculation for this exponent, I'm going to use a parenthesis to do that. Parenthesis, 0.0525 times 15. Close the parenthesis. Now, if you had multiplied that out a while ago, that's the exponent that you would have. Now I'm going to hit equal to complete this total calculation. And what I have here for A, 10989.47. Let me scoot that over. So in other words, $10,989.47. So if we're compounding continuously, we're going to use this alternate formula. What rate of interest is needed for $5,000 to grow to $12,000 in 10 years if interest is compounded continuously? Now again, I noticed that compounded continuously. So again, I'm thinking about that new formula, A equals P times e to the RT. 5,000 is our principal, isn't it? That's what we're going to invest. We want it to grow to 12,000. In other words, we want the final amount in that account to be 12,000. Our time is 10 years. What about R? We don't know R. That's what we're asked to find, isn't it? What rate of interest? Well, let's substitute into our formula and see what happens. A is 12,000 equals, our principal is 5,000 times E, R times T. Well, since I don't know R, I'm just going to say R times 10 is 10R. Now look at this equation. Notice where your variable is. It's up there in that exponent, isn't it? Now, recall we learned that if we have something times this E, the first thing we're going to do is divide by that 5,000 to get rid of that term right there. So those cancel over there. So let me just divide 12,000 by 5,000 right quick. And what I have over here is 2.4. So 2.4 is e to the 10r power. Now let's take the natural logarithm on both sides. The natural log of 2.4 is equal to the natural log of e to the 10 times r. Now we can bring the exponent down. The natural log of 2.4 equals 10 times r times the natural log of e. Do you recall, natural log of e is 1, isn't it? So that simply means I have the natural log of 2.4 is simply equal to 10 times r. And to solve for r, we just need to divide by 10. So what I'm going to do is to take my calculator and do the natural log of 2.4 and divide that by 10. And my display, let me just kind of jot, shows 08, 7, 5, 4, 6, 8, and some other digits. Now, we're going to round this interest rate off. Now, what I'm going to do, first of all, is I'm going to keep 4 decimal places here. So I'm going to keep 0.0875. The reason I chose to do that, remember when you have a decimal, you move your decimal 2 places to the right to change to percent. So that will give me 8.75%. Normally when I'm calculating this interest rate, I will at least get hundredths here when I'm rounding off to the nearest percent. Now, some textbooks will instruct you to round off in different places perhaps. And if you're not told, then it's sort of left up to you on where you want to round off. Again, what you see in this example is that working with this equation right here that we were given, this formula, because of where our variable was, we had to go back and use what we learned about working with logarithms to solve this exponential type equation. Now, we have talked about compound interest, compounding over different time periods, and so forth. The next concept that we want to talk about is what's called effective rate. Now, used to, when newspapers advertised for banks, you would see in those advertisements something like, we will pay 6% compounded quarterly. And then a lot of times, either in parentheses or in smaller print right below that, it would say something about this will yield or an annual effective rate of, and it would give you a different percent. What they're doing there is quoting what's called an effective rate. Now, I have defined an effective rate for you. Let's take a look at that definition. The effective rate is the simple annual interest rate that will yield the same amount as compounding for 1 year. Okay, let's talk about that again. Simple annual interest rate. That means if you were just quoted, we're going to pay you 6% at the end of 1 year. That's what we mean. And the effective rate is the rate for that one simple compounding that would give the same amount of money as our compounding rate would give. Now, I've put a note here. If interest is compounded annually and time is 1 year, then N is 1 and T is 1. So if you go back to this formula, if N is 1 and T is 1, then our formula simply becomes A equals P times 1 plus R over 1. Well, R over 1 is just R, and 1 times 1 is just 1, and we don't need to write that exponent. So we have this simple formula right here. So if you look at this form, P times 1 plus R, this R right here would be your simple annual interest rate. Okay? So let's remember that format as we look at a problem. What is the effective rate for 8% compounded monthly? The effective rate. Now, you'll notice here he did not give us a principal amount. I'm not going to worry about that right now. Let's go to our formula that we learned originally. A equals P times 1 plus R over N to the N times T. Now, I do not know either A or P, so I'm going to keep those letters in there. But I have 1 plus. What is my R? 8%, so that's 0.08. How often am I compounding? I'm compounding monthly. That would be 12 times a year, so that's divided by 12. Now, if I'm wanting to calculate an effective rate, I want my time to be 1 year. You'll notice he didn't say that, but we're to understand that from the definition of effective rate. So if my T is 1 and my N is 12, this exponent is going to be 12, isn't it? Now, I still have these variables, but I want to show you something here. Let's go to our calculator and do 1 plus 0.08 divided by 12, and then we're going to raise that to the 12th power. So what I'm seeing here is 1.08299, and it continues for some other decimal places there. Now, I'm just going to do one other little simple thing here. 1.08299, etc. is the same thing as 1 plus 0.08299, etc., isn't it? Do you see that? Okay, let me slide this little thing back up here. Remember what we talked about? If time is 1 year and N is 1 year, then our formula looks like this. So this is what we need to have effective rate. R is this effective rate. So if I say this is equal to P times 1 plus R, notice that the R is in the same position as that number right there. So my R is 0.08299, etc., etc. Now again, this is an interest rate, and so what I'm going to do here is just, I'm going to round off, and I'm going to keep 4 decimal places. That's these 4 right here. But notice, since that's a 9, I need to add 1 to this, so that would be what, 0.0830. If I compute that into a percent format, that's 8.30%. This is my effective rate. So in other words, what we're saying is being paid 8% compounded monthly is the same effect as being paid 8.3% compounded one time a year. A lot of times when you are comparing accounts that you might be able to put your money in, it's important to be able to come up with an effective rate. because if you're quoted two different percentages and two different compounding times, it's really difficult to compare those unless you convert them into an effective rate. Well, let's take a look at this equation. What is the effective rate for 6% compounded continuously? Well, notice this compounded continuously. For compounding continuously, our formula was A equals P times e to the RT. Now again, because I'm saying effective rate, my time is 1 year, isn't it? I don't know A, I don't know P, I have e to the R times T. R is 0.06, T is 1, so that's going to be 0.06. Now I'm going to go to my calculator and do e to the 0.06 power and put that down here. So I'm going to get to my e to the x. My exponent is 0.06. And what I have here is 1.061836 with some more digits. Now again, remember this can be written as 1 plus 0.061836, etc. So this number right here is my R. Okay, so R equals, if I round off to 4 decimal places, I have 0.0618, which converted to a percent is 6.18%. So 6% continuous is the same as 6.18% compounded once a year. If the effective rate for compounding daily is 7%, what is the nominal rate or the annual interest rate? Well, this problem is a little bit different, isn't it? Let's go back a second and remember that what we had was our amount is P times 1 plus R over N to the N times T. And we said if we're going to do an effective rate, we're going to let T equal 1. And what we're going to get over here is P times 1 plus R. Right? Okay, now I do not know my P, do I? Okay, that's still not going to be a problem. I'm going to come here, P. 1 plus. I want to know the nominal rate. I want to know R. I don't know it. The compounding is daily, so that would be 365 times. My N is 365, my T is 1, so that's 365th power. And over here I'm going to have P, 1 plus, now this R is my effective rate, which is 7%. Well, notice, I've got these two things equal. If I divide by P, those are going to cancel out, aren't they? So what I have here is 1 plus R divided by 365 to the 365th power is equal to 1 plus 0.07 or 1.07. Well, our problem here is to figure out how to solve for R, isn't it? Well, is there some way perhaps that we could solve for R? I suggest here that we think of maybe a similar but easier problem. Let's not worry about how complicated this is. What if that was a square instead of a 365 power? If you have something squared equals a number, can't you take a square root on both sides? What we're going to do is take the 365th root of both sides. In other words, 1 plus R over 365 is going to equal the 365th root of 1.07. Now, let's not worry about that just yet. We'll let our calculator worry about that. Now, let's subtract 1. So I have R over 365 is equal to the 365th root of 1.07 minus 1. Now, to solve for R, we're going to multiply both sides by 365, and this cancels. Now, I have an expression here for R. It's 365 times the quantity, 365th root of 1.07, subtract 1. Now, will our calculator do this 365th root? Well, there's several ways that you might perhaps do that. You may have a key on your calculator that will show you a key that looks like this. It says the xth root of y. If you have that key, then you can use that key. If you do not have that key, you can remember that the 365th root is the same thing, as 1.07 to the 1 over 365 power, and you could use your x to the y key. Now, let's see if we can calculate this. And again, I may suggest that you get your calculator and kind of play with it, and let's see if we can come up with the solution here. Okay, well, let's work inside here first. Let's see if we can do that 365th root of 1.07. Now, I've done that with my calculator, and I have like 1.00018, etc. You might want to check that. Now that I have this answer, I'm going to subtract 1, hit equal to complete that, and then I'm going to multiply by 365. And when I've done all that, I'm getting 0.06766, etc. Okay? Now, if we do like we did before and we round off to 4 places, then what I have here is R equals 0.0677, or approximately 6.77%. Okay? Now, problems like this can sometimes look rather bad because those numbers can get difficult. Of course, what made ours look really bad was that compounding daily like that made that number kind of weird. Again, I would really suggest that you play with your calculator. You may want to pause your tape at this time and see if you can come up with this same answer that I have right here. Another concept that we want to talk about on this tape is called present value. So I have a definition here for present value. The present value of $A to be received at a future date is the principal needed to invest now to grow to $A. In other words, this would be something like, you know that in the future you're going to buy a car, let's say, and you know that you're going to need $15,000 to buy that car. So what you're deciding is, how much money do I need to invest today so that at the end of my time period when I'm ready to buy that car, I'll have that $15,000. So let's look at a problem first of all and kind of deal with this, and then we're going to see that we can also work from a formula to solve present value problems. How much money is needed to invest now at 5% compounded daily if you want to have $5,000 in 2 years? Well, let's go back to our compound interest formula. A equals P times 1 plus R over N to the N times T. Now, for this problem, I do know what I want to have. I want to have $5,000. So what I want is for A to be 5,000. What I don't know is my principal that I need now. I don't know P. Well, let's keep filling in here. Do I know my interest rate? Yes, it's 5%. So 0.05. Compounded daily, so that's 365. And my N times T, this was 2 years, so I'm going to have 365 times 2 up there as an exponent. Now, if you look at this, of course, what we can do is calculate this with our calculator and divide into 5,000, and that would solve for P, wouldn't it? Let's just kind of run through that. I'm going to take my 1 plus 0.05 divided by 365, and I'll hit my equal to complete that, and then I'm going to use my x to the y to raise to the power, and the exponent is 365 times 2. Now I'm using a parenthesis around that part. Okay, and so what I have here, I'm not going to copy all of it, is 1.10516, etc. So I have P times this number equals 5,000. So I need to divide this number into 5,000, don't I? Okay, so one way that we can do that is that we can invert this using our 1 over x key and multiply times 5,000. And so what I have here is P equals 4524. I'm going to round off to the nearest penny. So we need $4,524.22. Well, you're saying that's almost the whole $5,000. Well, if you notice, we didn't have a very high interest rate here, and we were only doing this for 2 years, so this is a reasonable answer for that. Now, you might say, every time I want to do a present value problem, I don't want to have to do all this algebra. The thing that I want you to notice is that what we needed to do was to take this quantity and divide it over here. So in other words, we needed A divided by 1 plus R over N to the N times T power to solve for P, didn't we? Now, if you look at our formula that I'm going to give you now, present value formula, P equals A times the quantity, 1 plus R over N, notice to the negative N times T power. What did they do? Well, if you look at this, remember, if you have something down here in the denominator, if you move it up to the numerator, then the exponent changes to negative, doesn't it? And so if you compare these two, you can see that what we have is exactly the same thing. They've just chosen to write this using negative exponents instead of showing this divide right here. But actually it's the same formula. So the nice thing is that the formula resembles so much the compound interest in terms of this 1 plus R over N. The thing we need to remember is for present value, we make our exponent negative, and the A and the P actually switch positions. But you'll notice that these letters represent the same things that they represented in our compound interest formula. So now that we have this formula, let's see how we can use this formula to work another problem. How much money is needed to invest now at 8% compounded quarterly if you want to have $10,000 in 7 years? Well, let's kind of label things. Our interest rate R is 8%, 0.08. We're compounding quarterly. That would be 4 times a year. We want to have 10,000, so the amount we want is 10,000, and our time is 7 years. Okay? Now, our formula, as we've changed it, remember now P is over here, A times 1 plus R over N. The difference here now, our exponent is negative N times T. So let's substitute in this formula and solve for P. Our A is 10,000. We have 1 plus our interest rate, 0.08, divided by 4, minus N times T. Well, 4 times 7 is 28, so that's to the negative 28 power. Okay? Now, we can key this into our calculator. Let's put in our 10,000 times, I'm going to use a parenthesis here, 1 plus 0.08 divided by 4, close the parenthesis, go immediately to the exponent, x to the y, negative 28, and then hit equals to complete the calculation. And what I have here is $5,743.75 when I round off. Now you'll notice this looks a little bit better. We only have to have a little over 5,000 and we're wanting 10,000, so it's a little more than half that we need to have right now, but not quite so much. But you'll notice two things. We're waiting longer and we have a higher interest rate here. Now we can also do present value problems when we are compounding continuously. So let's take a look at that. P equals A times E to the negative RT. A is the amount after T years. P is the principal or present value. R is the annual interest rate. And T is the number of years. Okay? So let's use this formula and calculate a present value for continuous compounding. How much money is needed to invest now at 6.5% compounded continuously if you want to have $9,000 in 4 years? Now remember, our P and our A have switched places when we're doing a present value, and our exponent has changed to negative. So P equals A times E to the negative RT. For this particular problem, we want to have 9,000. Our A is 9,000. Okay, that's going to be a negative exponent. Our interest rate is 0.065. When we change to a decimal, our time is 4 years. Okay, so up here we have 0.065. times 4. Okay, well let's see if we can calculate this. I'm going to do 9,000 times, I'm going to get my E, and now because I'm going to do a calculation, I'm going to do a parenthesis here. I need 0.065 times 4, and I need that negative, and then hit equal to complete. My principal is about $6,939.46. How much money is needed to invest now at 6% compounded continuously if you want to have $8,000 in 5 years? Well, let's take a look at this. Compounded continuously, and this is a present value. We want to know how much do we need to invest now to have money later. So we want P equals AE to the negative RT again here. Okay, our A is 8,000. Our interest rate is 6%, so we have negative 0.06 times our T of 5 years. Again, let's go to the calculator. I encourage you really practice with that calculator on these problems. 8,000 times E to the, and I'm going to use a parenthesis again, 0.06 times 5, and I need that negative. I have $5,926.55 here. Okay, I have one last problem that I want us to look at just to give you a little bit of basis for some real-world problems that you might be interested in someday when you're making investment. A zero coupon bond, that means a non-interest bearing bond, can be redeemed in 12 years for $15,000. The question is, how much should you pay for the bond now if you want a return of 9% compounded semi-annually? Now what they're telling you is that in 12 years you're going to get $15,000. And see, the question is, how much should you pay now? In other words, how much principal should you put in now if you're going to get that $15,000 in 12 years? Now we're compounded semi-annually here. Did you notice that? So let's go back to the formula where we do not have continuous compounding. Our present value formula was P equals A times 1 plus R over N. We need a negative N times T exponent here, don't we? Okay, well we're looking for this P. We're going to get $15,000, so that's our amount, that's A. 1 plus our interest rate is 9%, so that's 0.09. If we're compounding semi-annually, that means twice a year, so we'll divide by 2. And our exponent is going to be minus 2 times 12, or minus 24. I'll just go ahead and put that in. Our N is 2, and our T is 12. Okay, well let's go to the calculator, and let's see if we can do this. Let's do 15,000 times, I'll use a parenthesis, 1 plus 0.09 divided by 2, close parenthesis, go straight to the exponent, negative 24, and hit equal to complete. My principal is $5,215.55. So if I pay this amount of money today and I get $15,000 in that 12-year time frame, then what I'm saying is it's equivalent to putting this amount of money in an account that pays 9% compounded semi-annually. This completes the lesson on compound interest. The primary reason for doing this lesson was to let you see types of situations where you use these types of exponential looking functions to solve the problem. I would appreciate it if you would rewind this tape before you return it. Thank you very much.